So hello students, welcome back once again to the online lectures over software application lab. Okay, so in today's session we are going to discuss about uh, how to prepare Excel spreadsheet for design of one lab. Okay, so again here we have the prepared Excel sheet. Okay, so in that we have to follow the steps from this Excel sheet, how to prepare how to develop a spreadsheet for design of one slab. Okay, so here again you have to first start with the page layout. In the page layout, first is you have to fix margins. Okay, then you have to fix the uh, orientation, so that is portrait. Okay, then size you select as A4. Okay, so when you select size A4, again you can see these dotted lines here. Okay, so according to this again I have told you that whatever you type, that should be within this dotted lines. Okay, so first, that is the design of one-way slab. So you can write and you can merge and center that. Okay, so these are the given data here, so you have to type again in separate cell. Okay, so I can, so here, okay, so it is given the shorter span, longer span, and the wall thickness, the slab resting on the wall thickness of 230 mm. Okay, then superimposed load is given, that is 4. Floor finish is given 1 kN per meter square. Characteristic strength of concrete FCK is also given, that is 20 Newton per mm square, and the characteristic strength of steel FY is also given as 415 Newton per. So here it is not meter square, it should be mm square. Okay, Newton per mm square, Newton per. Okay, then this also you have to make, it is Newton per mm square. Understood? So then, so you have to type everything in the Excel spreadsheet. Then we have next option is Ly by Lx. Ly by Lx, the ratio of shorter span by longer span. Okay, we have to check. We know that it is a one-way slab, but still you have to check whether it is a fit in the ratio or not. So that ratio is Ly by Lx. So here again you have to use these two, that is Ly by Lx. Okay, so how you have to do? You have to equate equal to Ly 7 divided by Lx is 3. So enter. So you will get this. You have to use again, you have to put the formula there. Okay, so here it is 2.33, which is more than 2. So we have to design as a one-way slab. Okay, we have to design as a one-way slab. So as I told you, the difference between one-way slab, two-way slab, we can differentiate based on the ratio. If Ly by Lx is less than 2, then you have to design as two-way slab. If Ly by Lx more than or equal to 2, you have to design as one-way slab. Okay, understood? So hence the slab is designed as a one-way slab. Now after that, for trial section, as we have discussed in the previous semesters also, that is, it is depth should be more than or equal to span divided by modification factor into the alpha. Okay, so that's why so here you have to use that. Okay, span is, you have to consider shorter span. You can see here you have to consider shorter span divided by so into 1000 to make it in mm, into the factor is used as the gamma is 20, so here it is wrong, so you have to type here 20. Okay, you have to type here it is 20 into modification factor 1.2 into modification factor 1.2. So we have to use the modification factor between the ranges 1.2 to 1.3. Okay, as I told you, you have to use between 1.2 to 1.3. So here it is used as 1.2. So from that you will get the depth as 125. Okay, so we will get depth as 125. So therefore D is equal to 125 mm. Then again, assuming 20 mm clear cover and 10 mm dia bars, you have to find out the total depth. Okay, so that is the effective depth plus clear cover plus dia by 2, so that is 25. So total together again the capital depth is 150 mm. Okay, so we got the depth of the section as the small d, the effective depth as 125 mm, and the total depth, overall depth is 150 mm. Okay, then after that same you have to type here as I discussed in the previous lab sessions, how to type and how to insert equations. Okay, then next is how the for bending moment calculation. Next is bending moment calculation. So bending moment calculation के लिए you should have the effective span. So again you type here effective span, and we have the effective span is L is the supporting wall thickness divided by 2 plus supporting wall divided by 2. There are two criteria for the calculation of effective span or the effective length. So that is L plus, that is center to center between the walls. Okay, so that is L plus half of wall thickness plus half of wall thickness. You can see here it is L plus half of wall thickness plus again half of wall thickness. Okay, then again L plus D, L plus effective D, so that is 3125. So we'll get these two. Okay, so you have to choose minimum between these two. Okay, you can check here. So I got 3000. You can check here 3000 is the span. Okay, you can click it here also, or you can type. Then wall thickness is 230 divided by 2 plus 230 divided by 2. Okay, then next for this L plus D, so we have got D is equal to 25 mm, so therefore it is L plus D. So you have to choose least between these two. Okay, so the length of the span is 3125. Okay, 3125 mm. Then load calculation. So load calculation, again you type self weight is equal to volume into density. So volume क्या है, BD into the density. Okay, you can check here. So here the total depth is 0.15 into, you have to multiply 1 for perimeter length. Okay, into density, and even B, so the self weight is B. So the, I think here it is not considered. So here you have to consider. Okay, so for the total depth into per meter length. Okay, this per meter width into 25. Okay, sorry. So here you have to multiply 1 into 1. Okay, so that is yes. So enter. So that is 1 is perimeter length I have multiplied into density is 25. Understood? Then next is the superimposed dead load, lie load is given as, how much lie load is given? Lie load is given as 4. So again per meter, so you get 4 km per meter, and even the floor finish is given as 1, so 1 km per meter. Then the total load you can add. So how can you add? Equal to this plus this plus this, enter. So you can calculate the total load like this. Okay, so then the factored load is 1.5 times the total load. Okay, so here you can again, how can you calculate that? So equal to, I'll show it here. So equal to this into 1.5. Okay, this way you can insert the formula. Then we have the bending moment WU L square by 8. So how we can calculate that again? Your mu is equal to WU L square by 8. So equal to, I can show it here, equal to, you have to start with always equal to, and the WU is 13.125 into L is, the span is, we have calculated the span is L. Okay, so that is you can take this as 3.125 square or raised to okay, you can check here. So WS by 8 you have to give, I have taken 2, so WS by 8. Okay, you can check here. So W W is this 13.125, L is 3.125 square, W is equal to 8. So we got the ultimate bending moment mu. Okay. Then after that we have check for depth. So by equating mu is equal to mu limit, by equating mu is equal to mu limit. What you have to do? Mu is we have got 16.02 into 10 to 6, okay, kilonewton Newton mm. So that is 16.02 into 10 to 6, that is in Newton mm, and Wu L square by the mu limit is 0.13 FCK BD square based on the grade of concrete. So our grade of concrete is M20 NFI 415. So our mu limit is 0.13 FCK BD square. Mu limit is 0.13 FCK BD square. Now what you have to do? You have to find out D. So how? Square root of. So you can find out the square root of mu divided by 0.13 FCK B. Square root of, you can insert the square root, or even you can, here it is given as SQRT in nothing but square root. So you can take that also, or we can make it like this also, equal to bracket of mu square root of that is mu divided by 0.138 FCK B. So that is mu is this divided by shift 0.138 into FCK is 20, 0.138 FCK, shift B is 1000, bracket complete. You can put again bracket here and shift raised to 0.5. So we'll see whether we'll get same answer. Well, we are getting doubt. Okay. Mu so mu we have got it as 16.08, that's why we are getting. So I'll click this into 10 raised to 6. I will see mu divided by 0.13 FCKB. Yes, so we got same answer. So earlier I was clicked here, so I was not getting answer. So now we can check here. So that is mu into 10 raised to 6 divided by 0.13 FCKB raised to 0.5, nothing but square root. Okay, so we are getting same answer. You can check. You can check this answer, and even you can check this answer. We are getting both the answers same. Okay, so then hence okay, because the D required is 76.18 and we have provided as 125 mm, so it is safe in check for depth. Okay, then next, area of reinforcement. So here no need to write the formula. If you don't have time, you no need to write the formula. You can write this also. You can write like this also. This is not required. If you don't have time, this is not required. If you don't have time, you can type like this also. Then you have to insert this into the equation. That is very important. You have to insert this in equation, which is very important. Okay, then after that, after inserting, we got the value of AST as 378.98 mm square. Then also you have to check for AST minimum, that is 0.12% of BD, because our grade is 415. For HYSD it is, the AST minimum is, for HYSD the AST minimum is 0.12%. Okay, and for this thing, 250 or for mild steel, the AST minimum is 0.15% of BD. Okay, so then we got AST minimum as 180. So our AST is less than AST. AST minimum is less than AST. So hence again okay. So now assume the diameter of bar. Then you check for spacing. Now to find out spacing again, area of one bar divided by total AST into 1000. That way. So 207. So we have taken as 200 mm. Okay. So therefore provide 10 mm die bars at a distance of 200 mm main reinforcement with alternate bender. Okay. Then distribution steel. For distribution steel के लिए again AST minimum we have to use as 150 mm square. Sorry, 180. We have to use as 180. Okay. Here it is. It is calculated as 180. So here, so please make a change. Here it is 180. Then assuming ATM die bar. So again spacing AST of one bar divided by total AST into 1000. So we got the spacing as 279, and we are going to provide 250 mm center to center. Okay. Then next is check for shear. Check for shear. The maximum shear force is again Vu is WL by 2. So you can calculate Vu is equal to WL by 2. So equal to Wu we have calculated as, you can click for that, Wu into L is 3.125. You can put bracket here. Divided by 2. Okay, so we got same answer. Okay, then therefore tau is equal to you have to find out the shear stress. Tau is equal to Vu by BD. Okay, Vu by BD. So you will get tau is equal to, this is also not required if you cannot able to write. So you can write directly here equal to, sorry not equal to, tau is equal to, tau you can insert the, see that symbol you can insert from here. You can go to insert option, you can insert symbol here. You can go to where you have to go, you have to go to insert option, and here you can insert symbols. So symbols, there are different symbols are available. So you have to search here where will be the tau. Okay, we have to search. So after searching you will get that. Now so this is again like tau. After searching you will get that. So right now we don't have that much time, so we'll go ahead with the this. Here you can search, here you will get the value. Okay, so that is tau v, we have to refer, you have to calculate, you have to get tau, symbol of tau. Okay, here if you find you will get so if you take this as tau, so that is also fine. So tau v is equal to Vu by BD. So you get tau v is the value of tau v as 0.164, and which is again less than tau c minimum. Tau c minimum is 0.28 Newton per mm square by referring IS 456 table number 19C. Okay, so we will get the value of tau c. So tau c minimum is 0.28 and our value of tau v is less than tau c minimum, hence it is safe in shear. Okay, it is safe in shear. So this is regarding how to create a Excel spreadsheet for design of one-way slab. Okay, so if you get any queries or any doubts in this while creating the Excel sheet, you can contact me. Okay, thank you.